Hello. The topic of this video is radiation exposure and protection. And I'm going to start in this first section by talking about some of the basic concepts: dose, effective dose, and so on. That will allow us to get into in the next section to get into looking at models of risk and talking about how to reduce radiation exposure through shielding and so on. But first, we need to have a common language to talk about this. So let's start with that. So the first topic to understand is dose and dose equivalent. We're going to start with the quantity that you're most familiar with, which is the dose, D. That's just the dose in gray that's absorbed. But that doesn't tell you what the biological effect of that dose is necessarily, because different particles will have different biological effects. For example, a photon has a different effect on tissue than a proton does, versus a neutron, and so on. So we need to weight the dose by some factor. So that factor is WR, is the radiation weighting factor, and that accounts for the relative biological effect of the particle, which of course depends on the LET, the linear energy transfer of that particle. Now, some notes on the units of this dose equivalent value, H. So the units are in sieverts, which is written SV. And you should note that an older unit is called the rem, Rankine equivalent man, and it's still in use, so you should know it. 1 sievert is equal to 100 rem. So here are some things to note about the radiation weighting factor. Number one, it depends on the RBE, as I said. It is defined by the ICRP, the International Council on Radiation Protection. And also, it's worth noting that it used to be called Q, which was the quality factor. That was an older term, and it's a term that's still used in the US by the NRC, Nuclear Regulatory Commission. So let's take a look at what these factors are for different practical radiation types. So here's a table of these radiation weighting factors. It's a little complicated because you have 3 different reports. These 3 reports agree with photons and electrons. The values are 1. They agree with protons, and they agree with alpha particles, but there is some disagreement about what the value should be for neutrons. But I think the essential thing here is to know that for photons and electrons, the value is 1, and for other particles, the value is higher. Now we come to the concept of effective dose, which is different than dose equivalent. Basically, effective dose accounts for the fact that the radiosensitivity of each organ is different. When it's exposed to radiation, it responds in a different way depending on what the endpoint is. And so you have to account for that. The way you do that is you take the dose equivalent in that tissue, H, which is written here as HT, okay, in sieverts, and you multiply that by the tissue weighting factor, WT. And then you do that for each tissue, for each organ, and you sum over all the different organs, and that in the end gives you a total effective dose. That's for the organism as a whole. So here is a table of these organ weighting factors. It's a little bit complicated because there are 2 different relevant reports, and these 2 reports don't agree with each other completely. So it's a little bit challenging to remember and retain, but these are the values, and you should know them. All right, so that concludes the basic intro. I'll leave you with a few further reading for the references. And then in the next video, we're going to get into risk from radiation exposure, how you model that, and also how you measure it actually in people. Okay.